Welcome everybody to the remote sensing session of the DDD conference. My name is Arnon Carnielli, and I'm the head of the remote sensing laboratory of the Institute for Desert Research at Ben-Gurion University. It's a great pleasure to have you to see all the colleagues and friends on board. The session today is focused on viticulture, in particular on studies that were conducted within the GRAPEX project. The project aimed at exploring vineyards evapotranspiration in order to develop remote sensing tools to detect stress and reduce water use. The project is funded by NASA and by the Gallup company, and all studies are conducted in the vineyards in California. We have today a 1.5 hour of session with 5 participants, 5 speakers. Each has about 15 minutes to talk and 3 minutes for questions. So please keep the time. So immediately I'll switch to the first speaker. This is Alfonso Torres Ura from Utah State University. So Alfonso, please.
Good morning, everybody, and thank you for the opportunity to share the research that we're doing in the, as Arnon mentioned, in the GRAPEX project using UAV technology. This presentation makes emphasis on evapotranspiration, but also on the information that is obtained from point cloud measurements done by UAVs that will help to characterize canopy characteristics, LAI, and how this information can be used for evapotranspiration and transpiration. You might be already familiar with UAVs. There are 3 types of them currently. On our left, we see the commercial available VTOL or multicopter that is the point of entry on UAVs. Sensors are available for them, scientific and commercial sensors, and typically they follow local regulations on their use. A second type of UAVs are called fixed wings. These aircraft can has a better performance in terms of altitude and scale. They could fly at higher elevations, so additional permissions might be required. Again, these are becoming more available commercially. Then there is a 3rd generation or a 3rd type of UAVs that we call it experimental, and they are just a larger version of the fixed wing. They are few in use, and mostly is an academy or industry. They require additional technology for their use, and in addition to better skills from the pilot. And these aircraft have a better battery endurance, a higher elevation, and also need a specialized or customized sensor due to the elevation that these aircraft are flying. I am part of the AGIR UAV program at Utah State University, and this has been a long-term program here at the university that has been aiming to push this technology, UAV technology, for applications on urban, environmental, and agricultural areas. And we explore commercial and experimental technologies that can improve and enhance the data collection using these unmanned vehicles. And as a comparison of what a UAV, a VTOL, and a fixed wing can collect in the same amount of time, if we look at this picture on the right side, we see a multicopter that can cover an area larger than 90 acres in around 20 minutes. A fixed wing at a higher elevation at the same time can cover 1 square mile. And that brings some economy of scale in terms of using different platforms or different UAVs for agricultural applications. As part of the GrapeX project that we heard on Monday and we will hear with the following speakers, we all have a same common goal, that is a multi-scale remote sensing algorithms and knowledge for mapping crop water use and stress. The different UAV technologies will be able to provide different area coverage, yeah, but all of them will be able to sample or characterize the surface, characterize the grape and interrow conditions at finer scales. And satellites will be able to provide a more large and more comprehensive view of multiple fields in the area. And this information, regardless of what UAVs or satellites, must agree or must be related with ground measurements by agronomist consultants and instrumentation that is deployed in the field. There is a great deal of variability in grapevines, and there is no farm that is uniform. And this is because local soil conditions, time of the year, cultural practices like the occurrence of interrow vegetation, and either by rainfall conditions or planting of these interrow vegetation, and time of the year. So this variability can be seen with UAVs at a fine detail that then we can use to characterize, let's say, grapevine scale conditions for evapotranspiration. This is a complex slide, and the major message from this slide is to summarize the evapotranspiration estimation process using UAV technology. We are favoring a model called the two-source energy balance model, the dual temperature or 2T approach. This model allows us to estimate the energy balance components that are happening at the interrow, at the plant scale, which are related with the water fluxes happening in these two conditions. This information is analyzed at a vine row spacing, and for this spacing, we have enough information to estimate, to quantify what is the canopy and the interrow temperature based on vegetation index and temperature maps. These models have proven to be very reliable and accurate when compared against ecovariance measurements. In the GrapeX project, we had the opportunity to collect UAV information along with ground information from different sources, especially the ecovariance measurements, across a climatic range of conditions from rugged, hilly conditions in Barelli to extremely hot climate conditions in Ripperdan and intermediate weather conditions in Lodi. And for all cases, we have found an excellent relationship between the estimations of evapotranspiration and energy balance components from the UAV versus measurements or estimations given by the ecovariance records. And so far, we have found that the two-source energy balance model has an accuracy of plus minus half a millimeter per day for evapotranspiration. So the two-source energy balance model can internally estimate or can separate interrow and vine water contributions to evapotranspiration. In 2018, Bill Custis evaluated the performance of the two-source energy balance for the separation or the estimation of transpiration. And he found out that there is a necessary improvement in the model given the differences between eddy covariance transpiration measurements versus estimated transpiration values from the two-source energy balance. And he found out that LAI was playing, or the accuracy of LAI was playing a major influence on the estimation of ET, and precise estimation or spatial estimation of LAI will be key to address these differences between ground measurements of transpiration versus the estimations given by the two-source energy balance model. So there is not a general LAI model that we can use. It has there have been in the literature, there have been efforts to use spectral information. Other efforts have been focusing on LiDAR or plant geometry efforts, but in both cases, the efforts have been local. They are not general enough. Therefore, a different approach was needed. So in our team, we developed an algorithm that we call it the vegetation spectral structural information algorithm, SIXIA for a lack of better name, that makes or combine the spectral and the point cloud information and address the topographic conditions in the vineyards, either slopy or flat terrains that can occur. This algorithm allows us to calculate parameters like the vine canopy volume or inter-row crop volume, surface area, height of these different two crops occurring across the farm. And these measurements or these estimations are related or are combined with spectral and thermal information. So these information allow us to do a comparison or a test of what has been reported in the literature regarding LAI estimation or spatial LAI estimation. We tested spectral-based approaches like reflectance and vegetation indices approach towards a general LAI model using the different data collection dates or IOPs of intense observation periods that we had in the GrapeX project. And we found out that using only spectral information is really hard to develop a general equation. Also, using only structural information, we saw an improvement on the LAI modeling. But it is when we combine both of them, structural and spectral information, that we see a better correlation between measured LAI or ground LAI measurements and the estimations provided by a model. And we see that improvements on LAI also play a factor or influence the estimation of the energy balance components and evapotranspiration. We see that with every improvement on LAI, the relationship between every component is better, the performance is better. So this gives us an idea. This is a work that we're doing these days, and we will continue next year. We are tapping the large archive of ground measurements, LAI ground measurements by the GrapeX project, and we are applying a machine learning approach. So a very intense, rigorous approach to estimate LAI estimations across the different locations where GrapeX was collecting information. And the preliminary information is showing good estimations or is showing a great deal of promise. And so this is something that we believe is going to help us improve ET estimations and also transpiration. And we're getting closer to the end of my presentation, and this is an example of how evapotranspiration and transpiration are provided by the two-source energy balance model. We have two examples here. On the left, we have a map of evapotranspiration and transpiration. I think I made a typo here, but the second map on the left is the transpiration ratio over the total ET. And we can see that the spatial variability is might be different than the variability shown in ET. Recently, in July, we flew over an almond site where we were able to collect information, and there were local meteorological information nearby, and we were able also to estimate UAV or plant almond scale evapotranspiration, and also an estimation of transpiration for almonds. So in clamped canopies like grapevines and orchards, the two-source energy balance model performs well, and what we are looking in the following years is to improve this partition or this separation of transpiration, because it holds a great deal of improvement for water management. For starters, we can see that it can help us to estimate or to provide information regarding net irrigation requirements, focus for localized irrigation systems that by removing the contribution of the interrow to the evapotranspiration, it can help us to redefine water use efficiency in terms of water applied versus water transpired instead of water or evapotranspiration. Also, the transpiration product can help us to estimate crop water stress versus thermal base or local measurements. It can give us a way to estimate this parameter without the need of local calibrations. And additionally, we can link transpiration estimation to surface atmospheric interaction studies, but also water carbon processes, the relationship with climate change. One last topic is that the information provided from UAVs on reflectance, thermal, and point cloud information can be used also to estimate yield production. And this is an additional project that we had with the GrapeX team, where we were looking the relationship between the pruning weight and fruit weight in grapevines with different parameters that can be derived by the UAV. We found out that there is no one single variable or parameter that can describe pruning weight or fruit weight, but a combination of them can reach good agreements between ground measurements, providing then a way to estimate a spatial yield estimation used at plant scale using UAV technology. So in summary, UAV technologies are a tool that is proving to be very useful to characterize plant and interrow conditions that can then be used to describe water and biomass conditions across the farm. And the models and the effort that we have been doing in the GrapeX project have helped to map especially water estimation. We found out that the model is working at that has an excellent performance, half a millimeter per day accuracy. So we are very confident on the model being used for commercial or practical applications, although we need to make an additional effort on the partition or the estimation of transpiration. And for that, an additional effort to estimate adequately LAI and characterize better the separation of soil or interrow and bind water fluxes is going to be necessary. And transpiration opens a different set of research and application opportunities from irrigation water management to land and atmosphere and water carbon processes. And these are very interesting topics to talk about and work. So that is my presentation, and I'm happy to answer any following answers regarding our work. This is a picture of the GRAPEX team in one of the intense observation periods with the Aguirre drone survey in the Lodi site in California. Thank you.
Thank you, Alfonso. It was a great presentation. We are very short in time because you use all your minutes. So I suggest that if someone has a question, please write in the chat with the email so Alfonso will be able to respond. And we immediately will move to the second presentation. It will be Feng Gao from the USDA ARS Hydrology and Remote Sensing Lab at Beltsville. Feng, the podium is yours, virtually.
Okay, thank you, Arnold. Let me start. Can you see my screen? I can.
Yeah. Enlarge it.
Okay.
Yeah, that's great.
Good morning, good afternoon. Yeah, my name is Feng Gao. I work for USDA ARS Hydrology and Remote Sensing Lab. And this presentation is going to talk about the satellite retrieval of Vineyard leaf area index at 30 meter spatial resolution. So I first of all would like to acknowledge our colleagues from USDA, from Ian Gallo and Utah State, and also Israel, who contributed to this work. As we know, the leaf area index is key biophysical parameters for grape vine growth monitoring, water use modeling, and it can be measured directly or indirectly from ground. It can also retrieve from using UAV, as we see from previous presentation, and also from satellite remote sensing. Currently, global leaf area index data product are available at 500 meter spatial resolution from MODIS and VIRIS every 4 or 8 days. However, the 500 meter resolution is too coarse for agricultural application at the field scale. Our objective is to generate a 30 meter resolution leaf area index from Landsat and the harmonized Landsat and Sentinel-2 data, or called HLS data. It's NASA data product. So we want to generate the area Landsat 30 meter resolution area that is consistent to MODIS area for modeling at a different scale. And we also want to, this approach can be applied to large area and also in the automatic processing mode. And the remote sensing retrieval, a brief overview, is basically you can get the leaf area index from a physical model or empirical approach. So the physical model is physical, like you can apply this model to the large area, but it's could be very complicated. And some models requires land cover information. And the empirical model is simple. It just builds a relationship between the area and VI. It depends on what kind of vegetation indices we use. And also depends on sensor, spectrum, response function, or bandwidth. And depends on land cover type. And the relationship developed between the leaf area index and vegetation indices for one area may not be applicable to other regions because that's a local model. Another approach was developed, it's called a reference-based approach. It's or called a hybrid approach. Is combine the result from physical model and empirical model. So the idea is we have some area product we can use, and we have surface reflections from fine resolution sensors such as HRS. So we can use a machine learning approach to learn the relationship between the area and surface reflectance at coarse resolution. Once this model is trained from machine learning, we can apply to the fine resolution and surface reflectance, and then produce a fine resolution leaf area index map. And the field measurement can be applied to validate the result, and also can be included in the machine learning. So those are two different approaches. One approach uses, like in example here, use modest area directly. And another approach is to combine the field measurement and the modest area. I'm going to talk about both approaches later. So the reference-based approach need to rely on the modest high-quality leaf area index retrieval. It comes from high-quality data from a radiative transfer model. So that's a physical model, or called main algorithm in modest area product. The assumption is that because the leaf area index has a nonlinear relationship to surface reflectance, as we see from this equation, the sum of the surface reflectance or the sum of the leaf area index at a fine resolution to coarse resolution, they are not equal for heterogeneous area. So we need to constrain our samples to pure homogeneous pixels to make this function equal. So the equal both of the is scalable. So make them the relationship at a different scale are scalable. And once we have 500 meter spatial resolution samples, we can generate a regression tree in the previous publication, and then apply this model at a 500 meter resolution to 30 meter resolution, because those are scalable at a different scale based on the homogeneous pixel. So that's rely on the existing area product and also Lancet or HRS surface reflectance. Graphics experiment, as you see from the first day and the previous presentation, it's led by USDA ARIS and working collaboratively with the Utah State and JKL and other universities and NASA. There are three sites, experiment sites. The Borden or Serraloma site was starting in 2013. And then the two additional sites, Borelli site and Ripton site, were added in 2017. So I'm going to use all the data from this experiment period for area mapping. For the Borden site, 2013, we used mainly rely on the Lancet data. And then the Borelli and the Ripton in 2017, we used a harmonized Lancet and Sentinel-2, and also for the Borden site from since 2017. So the reference-based approach was first applied over a Serraloma site or Borden site. So this example shows the Lancet area from early, middle, and late wine growth period in 2014. We have many clear Lancet SEMA and Lancet data observation. So that allows us to generate those daily area at 30 meter resolution. So compared to the field measurement in early time, this include 2013, 2014, we see the absolute difference is around 0.44. And from previous presentation, I noticed Alfonso has MAE, or it's around 0.3 to 0.37, around. So that's a little bit higher than the value from UAV. And this value is close to the modest RI accuracy. So this reference-based approach rely on the modest RI product. So we'll probably see the similar accuracy from this data product. So when we expand the model to other two sites in 2017, and the results are scattered, as you can see. This include all the measurement from 2013 to 2016 from Lodi, and then 2017 to 2019 from all sites, all three sites. Those field measurements include RI from different experiment period, as you can see. And some field measurement has not included cover crop. So we remove or filter those measurements that have not included the cover crop, and only keep those measurements include both vine and inter-row cover crop measurement, or if there is no cover crop. Okay, so that's a filtered result. We see we remove some lower value from measurement, but still we see the high cluster here, the Lancet or HRS underestimate leaf index. If we look at the individual sites, the Borden site, the Borden Serralama site, generally doing well, but underestimate some value in area value in the recent years. Borelli site agrees well, and Ripton site that's mostly underestimated for high area values. So since we have a field measurement, so we would like to see if we can train the regression tree model using field measurement alone. Those reasons, one of the reasons probably relate to the vine structure from different sites. So since we have a field measurement, so we want to establish, see if we can use the field measurement alone to generate a regression tree and see if we can capture this variation or variability of the RI measurement. So on the left side is the training using the field measurement. So this is kind of assessment using the samples. And we can see we can capture some high values if we just use the reflection from all bands. But when we apply this relationship, the model to the modest samples, this is the relationship between the RI generated from the model and modest RI are scattered. So this is because the modest sample actually includes many different land cover types other than grape vines. And the field measurement just focuses on the grape vine. And we see the correlation coefficient is pretty low for a modest. And that means this the data we generated that model RI is not consistent to modest RI. So the idea is like we can combine this field RI measurement. That's what I presented before. I think that the previous one is method 1. This is method 2. So we can combine the measurement from vineyard and modest RI samples to build a combined regression tree model. So the one important thing is consider the weight, because the winery in this area is covered probably by 2 to 3% of all land cover types. So it cannot be like overweighted. So we do the weighting balance to balance the field RI from vineyards and modest RI for all land cover types. And here is the result on the evaluation result. It's the evaluation of the samples. We don't have a lot of samples for validation. And then when we use this model and look at the individual site, so the field plus modest data correct the error from Ripton site compared to use the modest data only. And Borelli sites, they're similar, and a little bit of improvement for the Borden Serralama site. So mostly the model probably handles the data from Ripton site. Okay, using this model, we can apply to the recent observations from HRS that harmonized Lancet and Sentinel-2 data, and can be in the near real time. So that's a result from last week. Using the grain tree from combined field and modest samples, it captures spatial temporal variability of area for different land cover types. Let me go back and forth to show the animation. There are some grasses here, and those are orchard tree. Those are tree, and those are 2 experiment sites from graphics in Repdan. And we can see the spatial and temporal variability from the different time at 30-meter resolution. This is daily array data. And we also see some field in the north, south. I need to confirm that's removed, or looks like they shows a different pattern here. Another approach is using a reference-based approach. Has been implemented in the Google Earth Engine. So Yang can use the modest array samples, and a random forest approach is another machine learning approach, and generate a 30-meter resolution Lancet array in Google Earth Engine, because that's in all the data in Google Earth Engine, so it can be applied to a large area and generate the data quickly. So this slide shows the modest and Lancet 8 array in 2018. So this area includes the graphics side. It's here, it's a graphics side. And those are large new data area in the modest, because those are the urban area. I think that's Sacramento, city of Sacramento. Modest does not produce the leaf index over urban area, because modest depends on 8 biome type. And then the random forest in the Google Earth Engine can produce for all different cover types. So it fills a gap, as you can see from here. And she also compared the Lancet area retrieval to the ground observation. It looks like pretty consistent to our ground observation in Serloma or Borean site. So the paper is under review. The summary, the reference-based approach can produce 30-meter resolution array consistent to modest array product. It works better for the homogeneous large crops, and can include a field measurement to improve result. So the limitations is it depends on the modest array product. The modest array uses 8 biome type. So they have the homogeneous assumption in the model. So it depends on the accuracy from existing data product. And also vegetation structures we can see from different linear site may affect the retrieval, array retrieval. And also array samples distribution affects the machine learning. We need to avoid some overfitting to balance these samples from different range of array. And for future, I think the validation currently just to compare the field measurement to 30-meter resolution directly. Maybe not, it's not a best way to do. So we need to talk to the Alfonso, probably get a fine resolution array from UAV, or currently a small set like we have data from Venus and the planet, and generate a fine resolution array, then aggregate to 30-meter resolution to make them more comparable at pixel footprint. We may consider the clumping index from different linear side, consider a different linear structure from a remote sensing retrieval. And additionally, it's field measurement from different season is also important for machine learning, because machine learning cannot do much on the prediction, probably just based on the sample, what is the sample we have. Okay, so that's my presentation. Thank you.
Thank you very much, Feng. Really, we have to skip the question time and to move to the third speaker, which is with Kyle Knipper from the same group at the Remote Sensing Laboratory at the Bell Street. Kyle, please.
Thanks, Arnon. Let me see here. Does everyone see that? Okay. So thanks, Arnon. I'll be talking about the use of evapotranspiration toolkit for near real-time irrigation management and the advantages and limitations that came with doing this. Like the talks on...
We don't see your presentation.
Oh, you don't?
Okay.
There we go.
Okay.
Yeah, okay.
Okay. Go ahead.
Thanks, Arnon. So I already mentioned I'll be talking about the use of an evapotranspiration toolkit for near real-time irrigation management and the advantages and limitations that we found when doing so. Now, like the previous talks and the talks that were also on Monday, this whole project is part of the GrapeX experiment and project. I want to thank all those that have contributed to the project, and it's been a large success, and I think that's because of the team that's been involved so far. So a lot of the motivation behind GrapeX stems from the large economic value of wine grapes in California, which can reach up to $3.6 billion and are projected to increase in acres produced actually by 30,000 acres per year, according to our National Agricultural Statistics Service. Now, the issue with that growth is that California is experiencing and has experienced a fairly rapid decline in water resources, specifically groundwater resources, where a majority of growers are pumping their water for irrigation purposes. Now, on top of that, growers now must adhere to the Sustainable Groundwater Management Act, which was passed through the California State Legislature a few years ago, which requires governments and water agencies of high and medium priority basins to halt overdrafts and bring groundwater basins into balanced levels of pumping and recharge. So there's an economic need to maintain or even improve grape yield, but also a practical and what is now required need to decrease water consumption. So one of the ways that growers are trying to meet both of these demands is through improving irrigation efficiency by applying an optimal quantity of water that can maximize your productivity. And it's common knowledge in viticulture that grapes do not need to be irrigated at their full water potential during specific times of the growing season. So in fact, deficit irrigation or irrigating less than a known required amount can actually help in producing a higher quality grape. So growers want to know, what is this deficit amount and when during the growing season should I apply it? And if we can answer these questions, we can both save water and improve yield, which is a win-win for the grower. Now, one of the ways that we think we can improve irrigation efficiency is by quantifying vine water use via satellite-derived evapotranspiration, or ET, product that is available at both a high spatial resolution, so field scale, and high temporal resolution, so daily. And we think ET can be a part of this solution because, one, it's already been shown to be a critical part of improving the management of water resources because it is quantifiable. And two, growers are already using more or less some version of ET as a metric to monitor and prescribe irrigation, whether it be a crop ET or a reference ET value. So growers are comfortable with this value. Now, our method of deriving this satellite-based ET estimate is based on the pairing of an Alexi and dysalexi ET model. So Alexi is a multi-sensor thermal infrared approach to ET mapping. It couples a two-source soil plus canopy land surface model, so TSEB, with an atmospheric boundary layer model in this time differencing mode to map fluxes at 3 to 10 kilometer resolution using thermal band imagery and insolation data sets from geospatial or geostationary satellites such as GOES. Essentially, Alexi runs TSEB twice during the morning hours, once after sunrise and once before local noon. Then through the coupling of this atmospheric boundary layer model, it internally simulates air temperature at the blending height, which ensures that the air temperature is consistent with the modeled surface fluxes from TSEB. Now, because Alexi on the left there is restricted to a spatial resolution of 3 to 10 kilometers, we utilize dysalexi, which is the disaggregation of Alexi to obtain field scale ET. So we do this by running TSEB again, only this time we use thermal infrared information from higher resolution satellites such as Landsat or MODIS. And we hold that air temperature that was derived via Alexi constant when doing so. But the main thing to take away here is that our model is centered on the thermal infrared imagery and that we individually estimate fluxes for the canopy and the soil, which is very important when looking at canopy covers like vineyards. Now, the outcome of this Alexi-dyslexi process can be seen here. So what we have on top are dyslexi estimates for MODIS, which is the coarser resolution, and Landsat on the bottom, which is higher resolution. Now, the common trade-off in satellite remote sensing is spatial resolution for temporal resolution and vice versa. So MODIS, which can produce a daily product, is restricted to 500-meter resolution. And conversely, Landsat, which is great spatially, it's at 30-meter spatial resolution, is only available every 16 days. So ideally, we want that Landsat spatial resolution on the MODIS spatial scale. So in order to do that, we employ the StarFM fusion model, which calculates weights on the MODIS Landsat pair dates and uses those weights to downscale MODIS ET estimates to the Landsat scale in between those Landsat overpasses. Now, as part of GrapeX, we have 3 separate domains. They've been talked about quite a bit over the last few talks. Now, although there is a lot of science and information regarding just like the tower information of these GrapeX sites, I'm mainly just going to be talking about using them as validation techniques or just validation for the remote sensing model. And that's what you see here on the right is a comparison between the closed and unclosed observations. So closed is the blue dots, unclosed are the white dots. Our modeled daily 30-meter ET in red, and the red triangles are actually daily ET derived specifically on Landsat overpass dates. Irrigation is in black on the top and precipitation is in blue. And at a quick glance, this chart shows the differences not only in ET, but management at the sites. So at Borelli, our northernmost site, we see consistent both in timing and amount of irrigation. Borelli is also the coolest and wettest site, which is reflected in ET data. Conversely, at Ripperdan, the southernmost site, we see that ET estimates, both modeled and observed, are much higher, which aligns with the hotter temperatures in the region. And we also see that much more irrigation is applied in that southernmost region. But overall, there's a fairly good agreement between the model and observations, regardless of the large physical differences and climate differences between the site, which is promising. And in fact, statistically speaking, we can look at modeled values and the reporting average of RMSEs of 0.88 millimeters per day and mean absolute error of 0.70 when calculated over both those years over all 4 sites. And one of the as soon as it turns over, one of the benefits or main benefits of using these satellite information, as with UAV from Alfonso, is being able to look at ET spatially and look at spatial differences and heterogeneity, not only within the vineyard, but over large ranch sites that may be available, which provides growers with more tools. Now, where the rubber meets the road is transitioning this satellite ET product into something that can be used in operation. So in 2018, we designed an experiment that would hopefully help us answer this question or transition to an operational product. What we did was we selected an additional vineyard location located just a few miles east of our already established Ripperdan site. And this vineyard site is equipped with a variable rate drip irrigation system, which allows us to irrigate in very specific quadrants within the vineyard, and that VRDI equipment aligns with the Landsat spatial resolution. So what we were able to do was block the vineyard into 4 different sections, which you can see there, and impose different stress levels over those blocks. So we stressed the northern half of the block and did not stress the southern half of the block. And when I say stress, I simply mean that we withheld irrigation during the early growing season until those stressors could be seen in the satellite information. And once that stress was seen, then we commenced irrigation. No stress simply means irrigating at business as usual. So the walkthrough of the experiment, we wanted to provide irrigation managers with weekly total ET once a week, every week during the growing season of 2018. On top of this, we wanted to test whether or not our Latency, Dyslexy plus StarFM fusion model, which again is based on thermal infrared imagery, outperforms a business as usual approach commonly applied in the irrigation community. So this business as usual approach is based on the product of a crop coefficient, which you can see there, which is derived in our case from NDVI or visible near infrared data, and reference ET, which we gather from local meteorological stations. Running both of these approaches in parallel in real time will allow us to determine, at least in this specific case, which produces the most useful and timely information. And as an additional check, we also want to compare the operationally run model with the retroactively run model, because the retroactively run model is our current standard, and it's important to understand the differences between those two. So running operationally means we are operating under a latency and satellite data acquisition. So once the satellite physically flies overhead or over the site, it can take days to weeks for that said image to be available for download or even use. So, you know, we had to sit down with Gallo and figure out what this meant from an operational standpoint. So what we decided was that we would create a weekly total ET product that would be available on Friday that the growers could use to prescribe irrigation for the following week. This meant that we ran the model on a Thursday because of computing resources and the time required to physically run the model. If running the model on Thursday, the last available thermal image, which is from MODIS, was available on Tuesday. So we ran the Latency, Dyslexy plus StarFM fusion model up until Tuesday using all available thermal imagery, including both MODIS and Landsat. And then we took the ratio of modeled ET to reference ET on Tuesday and assumed that the ratio would hold steady during the final 2 days of the week, meaning that we multiplied that ratio, which was held constant, by reference ET values from local meteorological stations. And then we could simply sum it up and get a 7-day product and push that out to the growers. So that's what we did. It looked like this. You know, every week we were pushing out these maps. The Latency, Dyslexy plus StarFM fusion model is on top, and the business as usual estimate based on NDVI is on bottom. And following the growing season, you know, like I said earlier, one of the most important factors was determining if there was a large difference between the operationally run model and the standard retroactively run model. And here you can see that there was little difference between the two, which is great because it gave us confidence in moving forward with an operationally applied product, at least in this aspect and using this physically based model. Now, unfortunately, when we were looking at spatial differences, we started seeing larger differences between the operationally run model, which is on the far left there, the retroactively run model in the center, and the business as usual model on the right. And what we found was, and you probably already picked up on it, was the spatial differences, specifically between the northern half of the vineyard and the southern half of the vineyard. And we noticed that in the operationally run model, the differences between those two, that stress signal was picked up on the July 26th model run, where retroactively it was picked up on July 12th. And simply what was happening was July 12th was an actual Landsat overpass, and that overpass date did not become available operationally until July 20th, so one day after that next week's model run. So once we had the information, we picked up on that stress signal but that latency and thermal infrared information delayed us by 2 weeks. Now, we believe that we were even able to pick up on this stress signal because of the fact that our model is predicated on thermal infrared imagery. And what you're seeing here on the left is our Lexi-Dyslexi model on Landsat overpass dates and the associated land surface temperature. On the right is the business as usual method, so the crop ET, and then its NDVI on the far right. And what you'll notice is that on July 12th, when we started reporting this spatial discrepancy in the stress signal in the northern half of the vineyard, it is because of that thermal signature that we see it, and the NDVI is unable to pick up on it. And I already briefly mentioned this, but again, is because of the latency in the infrared product that we saw of fairly decreased or increased errors within our model and observations. So what you see is the absolute error between the operationally run model and the observed weekly total ET. And what we find is when you update your Landsat image, you see a fairly large decrease in modeled error. And this isn't surprising, you know, obviously if your Landsat image date is closest to the actual date that you're trying to model for, you're going to have a lower error. This simply states that increasing the error, or how important that the thermal imagery is to this model and how sensitive it is when comparing to observations. And Arnon, I have a few more slides on trying to fix this issue with Landsat analysis ready data sets. And but because of my time, I'm just going to flip through them. And if anyone has any questions, I'd be happy to take them.
Thank you, Kyle. I'm afraid that we are running again out of time, and we have to move to the next speaker, which will be Martha Anderson from the same group at the Remote Sensing and Hydrology Laboratory at Batesville. Martha, please.
Great. Okay, are you seeing my presentation?
No, just enlarge it to the full screen.
Okay. Okay, is that better?
Now it's better, yeah.
All right. Okay, well, thanks for allowing me to be in this session. I'm going to, just following on Kyle's talk, give a little bit more background on the methods that we're using to map ET over these viticultural landscapes using satellite remote sensing data. There's a large group of us working together on this at USDA ARS, but also want to acknowledge the full GrapeX team, many of whom you've heard today and on Monday. And we're all working really hard together on this. So the techniques we're currently using are inherently multi-sensor, multi-scale methods. And this allows us to place the moisture status of our vineyard of interest, the vineyard we're trying to manage within a larger spatial context in terms of regional water management constraints, regional climate drivers such as drought. So it can be very valuable to see this at multiple different scales. For operational management applications, routine day-to-day, this Landsat spatial scale, kind of the 10 to 30 meter pixel resolution, seems to be fairly optimal because we can start seeing some variability in moisture conditions, vine health conditions over the scale of an individual vineyard block. As Kyle mentioned and others have mentioned, the methods that we're using for mapping ET are based on principles of surface energy balance. So the primary remote sensing input are maps of land surface temperature that we retrieve from thermal infrared imaging. But critically, we also need visible near infrared surface reflectance data to define the land surface albedo, the vegetation cover fraction, leaf area index, which are also very important in the energy balance partitioning. So to date, Landsat has really been our kind of our gold standard for ET mapping at the field scale. It's collecting both the thermal and the visible near infrared data that we need to run the model. It's collected at the same time, same platform, under the same conditions, very well co-registered. But unfortunately, the temporal support of Landsat sometimes can be somewhat inadequate, 8 to 16 days, depending on how many Landsat are functioning at a given time. And that could be a problem, especially during rainier parts of the growing season when we're not getting a lot of clear shots of the land surface. So more recently, we've been trying to augment our thermal sampling with some other sources of kind of medium resolution thermal imaging. EcoStress, it's a thermal only instrument. It was launched to the International Space Station in June of 2018. Landsat-like resolution, really high quality land surface temperature retrievals from its 5 thermal bands, but we have to get the VNIR data from elsewhere. It doesn't collect those data. Currently, we're getting it from the closest overpass from the Harmonized Landsat Sentinel data set from NASA. And then we've also been experimenting with pairing some kind of coarser resolution thermal imaging from the VIRS sensor, the I5 375 meter band, with VNIR data from Sentinel-2. Sentinel-2 doesn't have a thermal sensor, so we're trying to use VIRS as a proxy on those overpass dates. Each of these sensors has a little bit different spatial resolution, as you can see on the right. Now, ideally, we want them all to be at the same resolution so we can kind of stack these images and create these ET data cubes that we need for operational management. So we've been employing a thermal image sharpening algorithm that was developed by Feng Gao, who you heard from a little earlier. It's a regression tree approach. It uses all the surface reflectance data available from Landsat or Sentinel-2 to spatially sharpen up the thermal imaging to that higher resolution, in this case 30 meters resolution. Our postdoc Jie Zhu has done a lot of work with adapting the data mining sharpener for these different thermal data sources and has gotten it to work reasonably well. Had to make some modifications to take into account varying degrees of misregistration between the thermal and the visible near infrared information. But she has recently published this work in an article in Remote Sensing of Environment. So using thermal sharpening and these multi-source thermal imaging data sets, we have tested the performance of this data cube construction over a number of different agricultural target sites across the United States, each of which has 1 or more flux towers in it to evaluate quantitatively the performance. I'm going to be focusing on our 3 study sites in California that support the GrapeX field experiment. And these are some examples of time series extractions from the multiple data sources over the flux sites in each of these domains. So here, this is from 2018. The blue circles are the daily ET from the eddy covariance towers. The red and green and yellow diamonds are direct ET retrievals from Landsat, sharpened VIRS, and EcoStress. And then the red line is kind of a fused multi-source daily time series. And you can see the different thermal data sources are reasonably consistent with each other in most cases. I'll zoom in here on the Ripperdan field site, Ripperdan 760. It's a Chardonnay vineyard outside of Fresno, California. And pretty clear skies generally in this area. So Landsat alone does a pretty good job at recovering the general ET curve during the growing season, except for maybe like in the rainy springtime area where we're not getting a lot of clear Landsat scenes. Now, EcoStress was launched in June, kind of mid-year. We have usable data from about July to September in 2018. And in this case, it really helped to better define the dip in ET that occurs right kind of around the veraison period where they're curtailing the irrigation amounts to inhibit the vegetation growth and concentrate more on berry development. And then here's the sharpened VIRS data further helps to fill in some of these temporal gaps. We're even getting a couple more samples in that rainy period. So some value there for combining all these different thermal data sources. Of course, The challenge is then you have the processing load just starts to balloon because you have to download all these other satellite data sources and bring them to consistency. And I'll get back to that a little bit later in the presentation. So over the course of GrapeX, we've been constructing multi-year ET data cubes using Landsat, using combinations of different thermal data sources over each of our GrapeX sites, Borelli to Lodi to Ripperdan, and using them to study water use patterns at a variety of different scales over time, from the field scale to the local scale to the regional scale, and how those patterns respond to changes in land management and climate. And so I just want to give some examples of some of the analyses we've done over this Lodi domain, the longest operating GrapeX site that we've been working with. This has been talked about many times today. In this area, we have two side-by-side Pinot Noir vineyards, both of which were instrumented with the eddy covariance tower. So we can look at the long-term performance of the model over time, and this is work that Kyle has done and published. The model agrees well with the observations at this site. The observations are the red dots in the lower panel. But additionally, the model is also able to give us a kind of an idea of the spatial variability in the moisture conditions across the vineyard block. And that's not something we can easily sample with in situ observations, very useful for precision irrigation, as Kyle has mentioned. So we can use the remote sensing data to look at variability at the block scale. We can also look at variability in water use around our vineyard of interest. And this is an animation that we'll play. Not seeing it, are you? Okay, well, it was an animation of the variability in water use over that area over time, and how the different land covers kind of turned on at different times as the irrigation proceeded through the, let's see if I can even get past this slide. Okay, there we go. Okay, so we'll skip over that. We can look at variability in water use patterns within season, but also from season to season. So these are maps of seasonal water use for the 2015 and 2016 water years. At this point, we're moving deeper into a multi-year drought that was encompassing the state of California. And some associated water use and water allocation restrictions. The patterns look pretty similar at first look, but if we look more closely, about in May of 2016, this alfalfa field was abandoned in its irrigation just south of our instrumented Pinot Noir fields. And about the same time, a center pivot system was turned down to the south of there. So the net change was kind of a zero net sum game between the years, but very different patterns in water use locally, which may be of use or of interest to the vineyard managers here. At a larger spatial scale, if we have information about, detailed information about crop type or land uses, we can start to do some regional scale water use accounting. And this is an experiment that we conducted over the Sacramento-San Joaquin Delta region, just east of San Francisco, also including our Lodi vineyard sites. And this was conducted in response to the Sustainable Groundwater Management Act, where they really wanted to start to do a better accounting of water uses to better manage the groundwater resources in California, especially during this big drought that was occurring. So we had available to us these detailed land use maps. We were able to use our ET data cubes over this larger area to do an accounting of water use by crop type, kind of a crop or a crop per drop analysis here. And it's kind of ordered in terms of from low water users, the urban land covers, the fallow fields, up to the higher water users, the almonds, the pears, and the rice. In this context, ET, water use per unit area, vineyards kind of lie in the lower half of the spectrum, and this is because the tendency towards deficit irrigation in wine grape production. But if we then weight this water use per unit area by the total land area that's occupied by each of these crop types, we get a different picture of the overall water use. And now vineyards is up here. There's been a rapid expansion in the installation of vineyards in California in recent years, and a big associated increase in water use. We also see some response of human behavior and grower response to the developing drought, with a shift away from high water use crops from 2015 to 2016 from the alfalfa and the corn crops, and a big increase in summer fallow. So just using this diagnostic water use information along with some land cover information, we can deduce a lot about grower response to changing conditions. So some good value in this Landsat scale ET information to date. As we're doing these analyses, we have been kind of limited in our capacity to create these data cubes to relatively small areas. And this is purely because of the limitations of our computing facilities that we have at ARS. Just a huge amount of data download and processing required. And we're hoping that this is going to get relieved to some extent in the near future with the opening up of the OpenET platform. And OpenET is a collaborative effort. It involves a number of federal institutions, USDA, NASA, USGS, also working with some academic institutions, some non-for-profit organizations. And the goal here is to port a number of kind of high-resolution ET remote sensing models to the Google Earth Engine platform, where the satellite data already resides, so that these models can be applied efficiently and quickly over very large areas, and that data can be then disseminated very efficiently to the end users, to the growers, and to the water resource managers. We're in the development stage right now. If you go to etdata.org, you'll get some information about the project and some of the partners. We hope to release the platform early next year. This is kind of a prototype of what it will look like. You get in there, you can choose the year, and you can look at the data either as gridded data or summarized within field polygons. This is a raster image, and you can view either a single model or an ensemble estimate out of multiple models. Currently, the coverage is only over the Western US, but if this is successful, we hope to expand the geographic coverage quickly. And here it is summarized into these field polygons. So let's zoom in over here, over our Lodi field experiment site. You can see, I mean, millions and millions of field polygons have been digitized. Zoom in even more. These are our two Pinot Noir, here they are, Pinot Noir vineyards. We can click on one of them. Oh, they're over here. And get the, is that right? Oh, whatever. And get the water use time series for that vineyard from one or the ensemble. Click on the other vineyard, get another water use curve. So the time savings and running this all in the cloud is just incredible, and also the ability to share these data sets with the growers and the end users. So that's what I'd like to talk about, a summary of some of the utility of the satellite ET data. We've heard about how it's useful for vineyard management, but it's also useful for placing the water use within your vineyard within kind of a larger regional context. So thank you.
Thank you, Marta. And if anybody has questions regarding the talk before and the next talk, please write in the chat. And if we have some time during the break, we will try to answer these questions. So the last speaker for today is Noah Hana-Levi from the Remote Sensing Laboratory at Blanchard Institute for Desert Research at Ben-Gurion University. This is the Israeli contribution, small contribution for the GRAPES project. Noah, please.
just a second, I'll just have to share my screen.
No, you are on mute.
No,
Okay.
not. Can you hear me?
Yeah, we hear it. We can't see the presentation yet.
Perfect. Just a second. Can you see my presentation now?
Yep.
Okay. So
Just go to full screen.
Is that okay?
No, not yet.
No?
Okay, now it's okay.
Yeah? Okay. So it's kind of a delay, I think. So what I wanted to talk about today is how I took the data sets that we've heard before Feng and Kyle and Martha talk about, and I was lucky enough to get access to this data. And what I wanted to do was basically try to derive or delineate management zones. In a specific vineyard in the world show today. So just a generally speaking, when we looked at this data, what just popped out for me was the strong spatial variability along with a strong temporal variability and temporal autocorrelation, and also right, the combination between them. And I thought that this could be a good opportunity to use spatial temporal analysis and quantify these spatial and temporal dynamics together. And if we're talking about management zones, maybe we should define them first. Well, these are generally spatially homogeneous subregions in a field. And classical management zones up until today have been most commonly been defined using several variables or one variable or usually more than one variable, but at a specific point in time. So if it's, I don't know, terrain related variables or soil characteristics or even you know, data from remote sensing, but it's usually from a specific point in time. So then a certain clustering algorithm would be applied on this multivariate data set, and we would receive this kind of management zone map, where each management zone has its own specific characteristics, and management could be irrigation or fertilization, pest management, but essentially each management zone should be treated differently. So using spatial analysis, agronomists would then have to go and decide on the right amount of water because management zones would not provide this information. And so when I saw the graphics data, what I wanted to do was try and define management zones using the time series of these images of crop characteristics. So first we used evapotranspiration as Kyle described it. And we, along with defining management zones, we also wanted to see whether these management zones had anything to do with spatial variability of other characteristics in the field, and also whether they are aligned with spatial variability of yield. So we did that, and then we wanted to also take LEI and MBVI and see whether, because these are much more practical sometimes variables to derive, we wanted to know whether they are also good enough to do this process and to get management zones using LEI and MBVI. So we worked in the Northern Sierra Loma vineyard, and I'm not going to talk about it because we've heard about this before. Just to say that we masked out areas that did not include vines. And so the data set that I asked Kyle or had access to was for 4 growing seasons between 2015 and 2018, and we decided to focus on the images that characterized the growing season, which was from March to October. So it's a total of 245 images per season, and so if we have 4 seasons, then it's 980 images in total. And so mainly what we did with ET was for each pixel, we had a time series, and I'm going to show it in a bit, but we did a time series decomposition, meaning that we then got information on each pixel regarding 3 different time scales. One is a long-term trend, the second is the seasonality, and the third is the remainder, which is kind of represents the daily variations in ET. And then we took each of these time series components and applied time series clustering. And after that, we wanted to know first whether the 3 maps are comparable spatially. And then we wanted to see whether they were affected by certain characteristics in the field. So we used several environmental variables to see the extent of effect that these variables had. And then we wanted to know also whether these management zones are effective to quantify yield variability in the field. So this is how a time series decomposition looks like for a specific pixel in the vineyard. So we have this evapotranspiration data for a specific pixel, and then this is kind of a moving average kind of thing, and essentially what it gives us is, let's say, this is the 2017 growing season, so we see that on average, we have higher ET values than, let's say, in 2015. And the seasonality just provides us like a mean seasonal kind of pattern, and the remainders is what happens when we take the ET and we subtract the trend, subtract the seasonality, and all we get is the daily variations. So time series clustering is it's a big topic. I'm just going to say a few words about it. Clustering is, in general, is well, in this process, we want to take the data and try to partition it into specific groups where the observations in each group are as similar as possible, and while the different clusters are as dissimilar as possible. But in time series, we don't have one value per observation or per pixel in our case. We have multiple values, right? We have time series. Each pixel is a vector of series or of values. And so we have this process in between, which is dynamic time warping. It's very common in time series analysis, and essentially it just helps us compare time series data even if the points in time are not aligned or are not synced. And then we use that to derive a dissimilarity matrix, which is basically for each pair of pixels, we have a specific value describing how similar these pixels are, and then using whatever clustering algorithm. In this case, we use the fuzzy c-means, but we then decide which pixel is assigned to which group or cluster. So after that, we took ET and LEI and NDVI, which this is just an example of a specific pixel again, and we wanted to know whether we get similar results regarding management zone maps. And also we wanted to know whether we can use all these variables to generate a multivariate clustering management zone map. So for the results. So first of all, we wanted to know the right number of management zones. So this is kind of silhouette index is a dissimilarity index. It tells us how well our clustering model performs. So it performed best using two clusters or 2 management zones. So that was the number that we went with for the rest of the analysis. And And what we see here is the management zones for the evapotranspiration, the trend component of the evapotranspiration. And the green area is cluster 1 and the blue area is cluster 2. And well, the first thing that pops up is that cluster 1 on average has higher values of ET than the blue pixels, right, in cluster 2. And the red line here defines the cluster center, which is approximately the average of the values of the pixels here. And what we see here is also the difference between these cluster centers. So what it gives us, or what we see here, is that in 2015, let's say, we have a much stronger difference between these two clusters than in 2018, where we don't have, where we have a very little, the difference is very small. And then for seasonality again, we see that we have, well, similar pattern as we saw before for the trend. And again, we see the temporal pattern for each of these management zones and the difference. And this provides us maybe an information on, well, in different periods within the season, what happens to the difference, or where in the season we see stronger differences between the clusters or the management zones. And for the remainders, first of all, we see that the model performance is basically 0, right? So it's, the clustering is we can't use it. So daily variations is not a good component to use if we want to partition the field into management zones, right? The difference also varies around 0. So so it's not good to use. That's basically what I'm making of it. So this is just visually to see the management zones of the 3 time series components. And here we see, this is a V-measure of spatial association between regionalizations. It's a measure that tells us how similar, spatially similar the maps are. And you see that for the seasonality and trend, well, yeah, they're quite similar. This ranges between 0 to 1, and remainder as well. I don't like to refer to it because it's, it doesn't say a lot, but we see that it's weaker. And these are the variables that we use, the characteristics of the field, and we wanted to see whether these variables had anything to do with the spatial pattern of the management zones. So what we used was elevation, slope, northness is like a proxy to aspect, topographic wetness index, soil type, and lithology. And we used the random forest classifiers to see which of these variables had the strongest effect or was the strongest contributor to the spatial pattern of the management zones. And we see that both for trend and seasonality, we see that soil type was the major contributor, followed by elevation. And then we wanted to see, well, this is the yield map for 2016, which was the only one that we could use because of, I don't know, biases or artifacts in the other maps of the other years. But this was good enough. So what we did is, well, in a simple ANOVA, or in our case, t-test, because we only have 2 classes or 2 management zones, and we wanted to know whether yield in the green area was statistically different than yield in the blue area for each of these maps. But ANOVA, one of the assumptions of ANOVA or t-test is that the observations are random, so we had to avoid spatial variability. So it doesn't really matter how, but we we had to have some sort of distance between the observations. So it was defined, we used a distance of 55 meters. So we ended up with 65 random samples. And what we see here is that for the 3 different components, the management zone maps, we see that cluster 1 was, the yield in cluster 1 was specifically different from the yield in cluster 2, meaning that maybe it was, it gives an indication on how well the maybe differential management could be carried out in this vineyard. And then for the analysis of ETLAI and NDVI, well, these are, I mean, we only had 1 map this time for ETLAI and NDVI, and these are how the maps look like. And well, first we see that ET has, of course, stronger variations, which resulted in a bit of a weaker clustering performance, but not, it's not too bad. And then we wanted to also compare right? The temporal dynamics of the cluster center of cluster 1, cluster center of cluster 2, and the difference between them. So this is what we see here. These, of course, are normalized, so we can compare. And the Kramer's V is like it's like a correlation for a categorical variable, for categorical variables. And we see here that LAI and NDVI are practically the same map, right? They got a 0.97, so high agreement, but ET and LAI and ET and NDVI, I mean, it's not too bad. 0.61 means that maybe LAI and NDVI are a good substitute for ET. And the Frechet distance is a distance measurement just to see how aligned these lines are. And we see, of course, that cluster center 1 and 2 for LAI and NDVI are quite similar. And well, what we did for the multivariate clustering, since NDVI and LAI are practically the same map, we decided to use only one, so it's a bivariate clustering. So we took ET and NDVI, and we used the PAM clustering algorithm, I'm not sure. But then we had this final management zone map using these two variables. And this is a nice step to take towards maybe using both time series of whatever variables we have and the, right, these things, right? The next step maybe would be to combine the characteristics of the field along with the soil the crop properties. So yeah, I'm getting to the end. So soil characteristics were strongly associated with this spatial pattern of evapotranspiration management zones, and well, also with the yield patterns. This is the first time I think that we not only get like the spatial characteristics of the field, but also the temporal patterns of each management zones, which could be quite helpful, I think. So yeah, and as we have higher spatial resolution sources, and I think it will, just we will get more as time goes. We can get finer spatial resolution and much more details to quantify these kind of things. That is all. Thank you.
Thank you, Noah. I'm looking at the chat box. I don't find any question in it. So before we're closing the session, I would like to thank all the speakers for their interested and the high levels of presentations. And our colleagues from the US have a great day, and for the rest of the world, have a good evening. Bye now.